Are you bad at Minesweeper? Do you find yourself randomly clicking squares in the hopes that you'll, by pure chance, manage to avoid all the mines in the grid? Good news! Grover's algorithm can help. In this episode of Qiskit in the Classroom, we'll learn about how this quantum search algorithm beats a classical brute force approach. Just 2 years after Peter Shor revolutionized quantum computing with his famous factoring algorithm, Love Grover discovered another, perhaps less flashy, but surprisingly far-reaching algorithm. Grover's algorithm solves what's called an unstructured search problem. Given a set of possible answers with no exploitable pattern, find the one that satisfies some condition. As we saw in a previous episode, Shor's algorithm works by exploiting deep mathematical symmetries. Grover's, by contrast, makes no such assumptions. At first glance, this may look like a weakness. Without any structure to exploit, the best it can do is a quadratic speedup, cutting the number of steps from n in the classical case down to the square root of n, rather than the exponential speedup that Shor's achieves. But this bug is also a feature. Because it assumes nothing about the problem, it works on pretty much any problem in which the best classical solution is the brute force guess and check method. In this episode, I'll walk you through how Grover's algorithm works by amplifying the probability of measuring the correct answer while suppressing all the wrong ones. Then I'll show you how to implement it on a real quantum computer using Qiskit. We'll even use it to solve a tiny Minesweeper grid. Finally, we'll look ahead at how Grover's algorithm could matter in the real world, from accelerating database searches to powering brute force attacks on cryptographic systems. The Grover's algorithm story starts the same as many quantum algorithms, with a black box and what's called the query model of computation. Inside the black box is a function we don't have access to. We can only feed it an input bit string and observe the output. In Grover's case, the function inside the box is a checker that determines whether a given input satisfies some condition. If it does, the function flags that state as the solution. Classically, we'd have to systematically input each combination of zeros and ones of the input bit string to see what the function returns. Each attempt is called a query, and on average, we'd need n over 2 queries, where n is the total number of possible inputs, to find the bit string that satisfies the black box condition. You might think of it like a bank of switches wired together in some unknown way, where only one combination will turn on the light. But if the function inside the black box is quantum, we can query it with quantum data, namely, a superposition of all possible inputs. Grover's algorithm shows us how to harness this parallelism, not to check all answers at once, but to iteratively steer the quantum state toward the correct answer. After around square root of n iterations, the correct state is very likely to be measured. This is a quadratic improvement over the classical guess and check method. So how does the algorithm work? For simplicity, we'll assume there's exactly one correct state, though Grover's can be generalized to find multiple solutions. Here's an example circuit of one iteration of Grover's algorithm with 4 qubits. First, a Hadamard gate is applied to each qubit. As a reminder, the Hadamard takes 0 to the equal superposition 0 plus 1 over root 2, and takes the state 1 to 0 minus 1 over root 2. Applied to all 4 qubits simultaneously, this creates an equal superposition over all 2 to the 4, which is 16 possible states, each with identical probability. Now the oracle, labeled ZF here, acts on this superposition. It marks the correct state by flipping its sign, turning its amplitude from positive to negative. This doesn't change any measurement probabilities yet. The next step will do that. Now diffusion. The diffusion operator is the sequence of gates you see here. A layer of Hadamards, followed by this gate labeled ZOR, and then another layer of Hadamards. Taken together, these perform a reflection about the mean amplitude. This has the effect of pushing the marked state's amplitude higher and pulling all the unmarked states lower. At this point, you might be wondering what Z-OR actually does. It's a phase gate similar to the ZF oracle gate, but this one flips the sign of every state except the all zero state, 0, 0, 0, 0. On its own, that sounds arbitrary, but sandwiched between the two Hadamard layers, it has the effect of reflecting each amplitude in the superposition around the mean amplitude. The first Hadamards change the basis, then Z-OR reflects in that basis, and the final Hadamards change the basis back. I've just shown one iteration here, but we can apply the oracle and diffusion operators multiple times to continue to steer the state closer and closer to the target state. Then finally, all 4 qubits are measured. If the circuit's done its job, the correct state will appear with a higher probability than any other. One picture I find extremely helpful for understanding the algorithm more intuitively is the geometric picture. For this, we need 2 pieces of information. First, note that we can decompose the initial superposition state psi into 2 components. The correct state, the one we're searching for, we'll call A1, and every other state lumped together we'll call A0. So psi equals C0 times A0 plus C1 times A1. This means we can plot these two as perpendicular axes in an abstract 2-dimensional space. And psi, being a linear combination of the two, will sit at some small angle theta to the A0 axis. Here, closer to A0, because at the start only a tiny bit of the state is in the correct component, A1. Second, we need to know that an operator of this form, 2 V minus I, reflects any state about the axis defined by V. To see why, consider what it does to 2 simple cases. So here's V. A state along V is left unchanged, and a state perpendicular to V gets its sign flipped. If you'd like to check those 2 cases yourself, pause the video now. Any other state can be decomposed into these 2 components, and the operator treats each accordingly. That results in a reflection around V. It turns out that both the oracle and the diffusion steps in Grover's algorithm can be expressed as reflections in this geometric picture. Remember, the oracle flips the sign of the A1 state and leaves everything else alone. That's the same as a reflection around A0. So our state moves down here. It's a little trickier to see how the diffusion operator is also a reflection, so let's do a little math. We know that the diffusion operator is H times Z-OR H. Z-OR by itself is a reflection around the all zero state, since it flips the sign of every state that's not all zero. So this can be written as 2, 0, 0 minus I. The Hadamards surrounding this reflection are effectively a basis change, changing the axis about which the reflection occurs. Remember that H changes the state of all zeros to the state with an equal superposition of all states, which we label U here. So apply the Hadamard basis change, and the state just changes to U. And an I sandwiched between Hadamards is still I, since Hadamard is its own inverse. So this stays I. So the expression just becomes a reflection about this U state. So now our state moves here, which is an angle 2 theta from the original starting state. Each successive iteration of Grover's algorithm will rotate by another 2 theta. Remember, our goal is to rotate the state to be as close to A1 as possible. So we can do a little geometry to figure out the optimal number of iterations. In the reasonable approximation that theta is small, that optimum is the closest integer to the value pi over 4 theta, which is the same as pi times square root of n over 4. I'll leave it to you to check my math. This is where the famous square root of n speedup comes from. We only need square root of n rotations to reach the target, rather than the n checks that a classical search would require. Note that if you apply too many iterations, you rotate past A1, and the probability of finding your target state will start to decrease again. So finding the optimal number of iterations is crucial. Now we're ready to use Grover's algorithm on a real quantum computer. For this first activity, we'll decide on a target state that we want our algorithm to find, then make an oracle that flips the sign of this state. Here we pick the 4-qubit state 1110. To make the oracle, we can use this multi-controlled Z gate here from the Qiskit library. This gate will flip the sign of the state with all ones and leave everything else unchanged. So to flip the 1110 state, we just need to sandwich this gate between two X gates applied to qubit 0. The first X gate changes our target state from 1110 to 1111, which the Z gate then flips. Then the second X gate changes the state back to 1110, but now it has a minus sign, exactly what we want. Now that we've defined our oracle, we just need to know the optimal number of iterations to find the marked state. In this case, that number is 3. So we apply our Hadamard's to prepare the superposition, then apply the Grover operation 3 times and measure. After defining our backend and optimizing the circuit to be run on hardware, we can then send the job to the quantum computer. We set the number of shots to use here and view the results. As expected, the state 1110 is much more likely to be measured than any other state. We just successfully ran our first Grover circuit. But by now you may be asking yourself, what good is Grover's algorithm? We just used it to find a state that we already knew because we had to know it in order to build the oracle in the first place. And that's a fair objection. The logic definitely seems circular. I have a few things to say about that. First, the query model of computation was never really designed to be practical. Its purpose is theoretical. By separating a problem into 2 parts, the oracle and everything else, it gives us a clean way to analyze algorithmic complexity. How hard is the search, given that verification is free? How do the number of queries scale with the size of the input? These are useful questions even if no real system works exactly this way. You can also think of it as a 2-party activity. Your friend knows the target state and builds the oracle that flags that state. Your job is to find the answer using the oracle as a black box. No peeking inside allowed. And if you have a friend and you head over to the module on the IBM Quantum platform, you can do exactly that activity. But even if the query model is an abstraction, the mechanism behind Grover's, which is called amplitude amplification, is an extremely useful subroutine that shows up again and again in quantum computing. So while this demonstration may seem circular, what we've really been building is an intuition for something much more broadly applicable. And finally, there is a way to code an oracle without cheating. The key insight we need here is that there exists a whole class of problems for which it's very hard to find a solution, but for which, given the solution, it's very easy to check that it's correct. Factoring is an obvious example. Given a product of 2 primes, it's really difficult to figure out what primes those are, but once we know them, we can easily multiply them together to check the product. Now we have a better algorithm than Grover's to solve the factoring problem. See the video on Shor's algorithm. But this is far from the only problem that has this feature. Sudoku, 3-sat, Minesweeper, they're all difficult to solve, but easy to check. Why is that relevant to the oracle? That means we can know all of the conditions and requirements that a solution must satisfy, and we can code those requirements into a quantum circuit that we call the oracle. But just because we know those conditions doesn't mean we know the solution. Grovers will find the solution for us. To show you what I mean, let's take a look at the classic game, Minesweeper. In this easy 9x9 Minesweeper grid, we have 81 squares, 10 of which have mines hidden on them. That means that there are 81 choose 10, which is nearly 2 trillion possible configurations. And that's easy mode. Now, the grids that you'll get in a game like this are specifically designed so that you can use logical deduction to solve them. But in general, a random grid would require some guessing and checking. And when you hear the term guess and check, think Grover's. Grover's algorithm is designed to run on a perfect error-free quantum computer, so we can't really run it at scale yet. We can't use it to solve a 9x9 Minesweeper grid. Instead, as a toy demonstration, let's use Grover's to fill in this tiny Minesweeper grid here. Here we have 3 blank cells. The numbers here tell us how many mines are touching each corresponding cell, which places conditions on which of the blank cells have mines and which don't. This is such a small problem that by now you've probably already solved it in your head, but let's pretend we need Grover's to solve it. We'll code the conditions into a quantum circuit that will be our oracle. This one cell here says that either x0 or x1 has a mine, but not both. We can express this as a Boolean function x0, xor, x1, where xor is the exclusive OR gate. It returns true if either x0 is 1 or x1 is 1, and false if they are either both 0 or both 1. Same with this other cell, x1, xor, x2. Now this 2 cell says that there must be 2 mines hidden among the 3 cells touching it. The Boolean expression for this is given here. The XOR operation is essentially a parity operation, returning 1 if there are an odd number of mines and 0 if there are an even number of mines. We want there to be 2 mines, which is even, so this returns 0 or false. So we flip the whole expression with a NOT gate. Note that 0 mines is also an even parity state, but this was already ruled out by the other 2 conditions. Now we require that they're all simultaneously satisfied by joining them with AND gates. Now we need to encode this Boolean expression into a quantum circuit to make the oracle. To encode this on a quantum computer, the quantum version of an XOR gate can be accomplished through this series of C0 gates, and the AND gate can be accomplished with the controlled Z operator we've already been using. Here, this controlled NOT operator sandwiched between 2 Hadamards is the same as the controlled Z operator. So, if we introduce 3 extra workspace qubits, we can store the outcomes of each of these 3 expressions into each of the qubits, then ensure they're all simultaneously satisfied with the multi-controlled Z gate. This will flip the sign of the state that puts all the workspace qubits in the state 1. In the final step of the oracle, we need to reset the workspace qubits back to the 0 state so that they're ready for another Grover iteration. We do this by uncomputing, undoing all the steps except that final controlled Z gate. Then we can just call Grover's algorithm as before, but this time we need to specify which qubits we're using to define the search space, leaving out the workspace qubits, since their job is done. The optimal number of runs is 2, so we set that, optimize and execute as before, and we find that the 1, 0, 1 state is by far the most likely state to measure. That means the mines are here and here. We did it! We used a quantum computer to help us solve a tiny game of Minesweeper. Today, we walked through how Grover's algorithm works and why it beats a classical brute force search. We implemented Grover's algorithm on a real quantum computer and even used it to cheat at Minesweeper. Now, this demonstration was cool, but by itself not very earth-shattering if it only applied to Minesweeper. But tons of problems, including some very interesting and relevant problems, can be expressed in the same way we did for the Minesweeper grid, by converting constraints into Boolean expressions, then implementing them in a quantum circuit. This method could be applied to solve the toughest real-world problems for which no solutions exist other than a brute force search. One tangible example is hash preimage search. Hash functions convert sensitive data like passwords into fixed length strings called hash images. They're deliberately non-invertible, so the only way to crack one is brute force. Grover's algorithm would cut the search time to its square root. That sounds alarming, but a square root speedup is far less devastating than an exponential one. We just need to double the length of our hash images to compensate. And that pretty much gets to the heart of Grover's algorithm. It's general and powerful, but not exponentially so. To explore Grover's algorithm yourself, head over to the module on the IBM Quantum platform and try it out. See you next time.